It'll flash once in a while.
Oh, well, never mind.
Okay, we're gonna get going, and obviously we're here at Cruise. A couple of years ago, Mike uh, helped me out, and we put a drone up over the aeration basin, flew over one of the trains just to kind of get a bird's eye view. Then aeration basin over the secondary clarifiers. Of course, the birds that live out there didn't like it, so they were trying to attack the drone as we came back. I almost hit that light stand. That was nice to not lose the drone over the basin. But this just giving you, for those of you who haven't been into the cruise plant and walked around, give you a kind of a view of what we're looking at. We're now going from the secondary clarifiers, and we're going to fly back toward the aeration basin. So we're going in the reverse direction that the flow goes. Okay. And this is one of 12 trains, and these started out as a conventional activated sludge system that was by a manipulation then of the DO and the SRT. DO, dissolved oxygen, SRT, sludge or solids retention time. In other words, the sludge age, the average length of time a biological cell resides in the system. That concept of sludge age is something then that we will be leveraging as we go in terms of manipulating microbiology. All right. So in treating, we're going to kind of do the ABCs of wastewater treatment to begin with. For those who are just beginning in the business, I like to remind ourselves that we're handed kind of a batch of soup. We're going to call it wastewater effluent, or if it comes out of the primary clarifier, it will be the primary effluent. A batch of soup that's full of contaminants, and there's a fate of those contaminants. So we're just saying what comes in has got to go somewhere. And our job is to get out what others put in almost to perfection. Now, our discharge permit does allow some pass through, but we have very limited freedom to pass through very much. So we track the fate of contaminants. And so what comes into the plant has to go one of four places. It may go off to the atmosphere. In other words, that's what we call volatilization, right? Some compounds might be a very low molecular weight. They might actually just airstrip and they're gone. Other compounds would be largely removed by some biological mechanism. I'm pointing to biodegradation as a pathway, and this is really what we're going to be exploiting in the course. Biodegradation is a comprehensive term that implies that there's some also biosorption or a sticking to biological material of contaminants, and then the degradation part means that they're taking those apart for some reason. Now, bacteria take things apart for basically one simple reason. Now think about it. Why would a bacterium degrade something? What's in it for the cells that we grow?
Fuel source?
It's a fuel source. It's energy, right? So it's all about energy liberation and energy transformation. The bugs need the energy because bacteria know how to do two things. One is eat, the other is reproduce. And that's all driven by having enough cellular energy to do that. And so we're leveraging this idea that degradation is a natural phenomenon that will occur, and we're going to be trying to then enhance the removal by degradation of different constituents. Now, in the early days, wastewater treatment was largely going after the degradable compounds that cause an oxygen demand in the wastewater. We call that the BOD, right? So BOD, biochemical oxygen demand. You see it has BOD with a little subscript 5, simply means that the test was run for 5 days. It's a 5-day test. It has, it's kind of universally been used to express the organic content of wastewater. And from an operational perspective, it's the test we love to hate. We love to hate it because we get answers long after they're very useful for making operational decisions. And of course, then we look for ways to substitute something, a test that will give us an estimation of the degradable component, the oxidizable component, much more quickly. Anybody know what the alternative to BOD is that we use to estimate the organic load? COD, right. Chemical oxygen demand. 2 or 3 hours, you've got an ability to get something that estimates that degradable load. So the biodegradation component is what we fashion the DNR course around. Now we're also now going after nitrogenous compounds and transforming those, and phosphorus compounds and transforming those. And they were always being removed to some degree when a bug was eating BOD. There was also always some nitrogen and phosphorus that was being removed. But in municipal wastewater anyway, there's typically way more nitrogen and phosphorus than there's a biological need when carbon is removed. And when I use the term carbon, I'm using that synonymously with the BOD or the COD component. So if I say carbon or say BOD, I mean the same thing, okay? So in municipal wastewater, there's relatively a lot of nitrogen and phosphorus to the amount of carbon, and the bacteria then that we're leveraging for this degradation mechanism are going to take up some of that nitrogen and phosphorus to build the kind of cells that they need to build. Turns out we can grow and adapt certain microbial species that can take up the excess nitrogen and convert that. And let's see now, why was a cell taking up something? What did it get? Energy, yeah. So the nitrogen transformation is because there are bacteria that actually get some energy out of transforming nitrogen, and that there are some unique organisms then that have the ability to extract energy, cellular energy from nitrogen transformation, and that gives them a competitive advantage. Organisms are only going to populate the niche or the culture that can hold their own, which means they basically get the nutrients that they need and the energy that they need to replicate at a faster rate than they're dying out or washing out. All right. Likewise with phosphorus. The phosphorus transformations are also occur because, let's see, what is it that bacteria are looking for? What does the bacterium need to survive? Food or energy? And the phosphorus piece actually plays a pivotal role in certain species in allowing them to sequester or to store up energy containing compounds. And so we've figured out how to adapt microbial species that have enhanced abilities to remove both carbon, nitrogen, and phosphorus, and do so in proportion to what the excesses otherwise would be that would cause that to go through into the final effluent. So kind of a long-winded way of talking about the biodegradation piece here, but that is a good part of where our work is going to be done. I tip my hat and I bow deeply to my solids handling brothers and sisters here, because ultimately, whatever we remove, if it's not volatilized or degraded to some byproduct that leaves through respiration, which is typically carbon dioxide or nitrogen gas that might volatilize off an aeration basin, it's actually, we're tucking it into the sludge and moving then the contaminants through the solids handling side. So sludge handling typically ends up being the ultimate removal of the contaminants. We're not transforming, we're at least absorbing or bioabsorbing and moving on through solids handling, okay? All right, so whatever doesn't strip to the atmosphere, gets stuck into the sludge and degraded, or sent off to solids handling and removed that way, ends up in the final effluent. And this is where our permit holds us account, right? So that's kind of the, you know, the fate and transport of the contaminants is what we're designing this course to teach. Now, our goal as operators is to achieve some sort of optimum treatment. Well, that's kind of a throwaway concept on its face, but in reality, it is about that. That the optimum treatment isn't a straight path, as you very well know. We get rain events, we get industrial contributors, we get all kinds of curveballs sent to us. We don't know what's coming down the sewer, and so as operators, we want to have a design flexibility and the operational skill set that says, okay, we want to try to stay in some optimum piece, but this thing, our road is going to move. We're driving on a windy road. All right. So we do that by maintaining what we call a continuous culture. A continuous culture of microorganisms that produces a compliant effluent, right? We're going to meet permit. And let's remember, it's at the lowest possible cost. There is, like it or not, whatever level we are in the organization, in today's world, a responsibility that comes with the job that's not probably stated in our job description. And that is that we are mindful that what we're doing has tremendous value and it has an associated cost. And economics ends up being one of the things that we have to be mindful of and manage to the best of our ability. So I'm simply saying things like optimum treatment means make the effluent as good as we can make it and keep it as stable as we can make it. And let's make sure that when we're using DO, that the cost of the DO, which can be significant, is really applied as precisely as we can apply it. Because this is hundreds of thousands and or millions of dollars of delta with no measurable difference in outcome in a lot of cases. So there's big money at stake on oxygen adjustments. We have big money at stake on the cost of disinfection, perhaps, if we're using chlorine. And there are little glitches that can occur where we don't have optimum treatment and our cost of chlorine goes up. And we can go right on down the line. So this looks like kind of a throwaway sentence at the bottom, at the lowest possible cost. We don't have to lose sleep over that. We can lose sleep over a lot of things. I just like to have it in the back of our mind that what we're doing is delivering value to the utility, to our ratepayers, and to ourselves to do the right thing with the resources that we have. Okay? Now, the video clips that are running here on the side are just saying, yeah, and this continuous culture is biological. It's a live thing. It's a live and evolving culture of microorganisms that are always adjusting to the conditions in which they find themselves. And by the way, I'll say to my friends from North Texas, that's out of Wilson Creek, this little video clip here. So I tip my hat to you. I don't normally recollect where things are from, but I remember taking that video in preparation for the training that I did with you folks. And it was a nice example of a very good flock and a viable curricularia, and so I'll compliment you. So a little bit of the family album there. So we use a lot of jargon, right? So if we say the term bugs, and I use the term bugs kind of collectively, what we're referring to are the microorganisms that are in the activated sludge system. And it's largely the bacterial mass that's important. It's the bacteria that do the lion's share of the transformations that we're talking about. There are also protozoa and metazoa, the big bugs that are certainly in there. They don't know that they're treatment organism wannabes, that they're posers. I kind of denigrating some of my best friends here that live in that world. they're certainly contributing in a minor sense to the scouring up of free bacteria and other particulate. So they perform a valid function, but the real heavy lifting, and when it comes to the DNR process, it's all at a bacterial level that the relevant discussion should take place. Now, we do look at the higher life forms as kind of a reflection of the health of the underlying bacterial mass, which is pretty nondescript. So if we look at, and for those of you on the internet, you're not going to see this, but I'm holding up a sample of mixed liquor in a beaker. This is out of the cruise plant, so we know it's some of the finest activated sludge anywhere in the world, much less Texas. But in any event, you know, what we see there settled in the beaker is largely bacterial mass. And it's like, yeah, it looks pretty unimpressive. How many people live on planet Earth right now, if we took a head count? About 8 billion. Yeah, about 8 billion people. There's a lot of flavors, aren't there? There are a lot of different kinds of people. And isn't that the most wonderful thing in the world? That there is such diversity in that 8 billion. Because we contribute to a community that requires all sorts of talents and skills and capabilities. How many bacteria do you, so I've got a half a liter of mixed liquor here. How many bacteria do you suppose is in that beaker?
6. That's mine.
Millions.
Trillion.
A trillion? Yeah, you're there. You're right there. You know, there's certainly 10 times to 100 times the number of bacteria in that one little liter as there are people on the planet. The point being, we have a very high population density. And the bacteria that we're talking about, you know, we represent them here in our graphic as, oh, you have this little single cell and stuff goes in and it does things and stuff comes out. And the fact of the matter is there are many different species in there, right? And one of the things that TRA has invested in is a fair amount of genomic testing. You've used DNA techniques, you've used a variety of very advanced analytical tools to actually characterize the makeup of your microbiology. Turns out that there's, in that trillion bacteria that live in that culture, there might be 200 or 300 completely different species. Wow. Why are there so many different species, much less so many just sheer numbers? What is every single one that's in there getting? Why is it there? Why did that species make it? Found something to eat that it got energy out of. Yeah. Yeah. It's taken something apart, extracting energy and making energy to have a family, right? It built its numbers up, and we can do the DNA analysis, we can do different genomic testing and find out that all that's true, right? So we're dealing with very high numbers, very high species diversity, and that's a good thing. What do the bugs do? Well, the bacteria degrade the VOD, that's the carbon, and they produce flux. Now, on the right-hand side of this left-hand part of the graphic, for those on the internet, is dispersed bacteria, and on the left margin here is a flock. So bacteria will grow in either a dispersed or a flocculent form, and of course, they do both. Ultimately, what we rely on then is having the growth rate and the characteristics of that growth convert into a flock that actually will form. So we use the term flock to refer to the fact that bacteria at the right phase of growth end up clumping, and then they can be captured. The Achilles heel of an activated sludge system is liquid-solid separation. Now, what do I mean by that? Remember when we flew over with the drone, it was the aeration basin was aerating and treating, and then it goes to a secondary clarifier. Well, everything is in a suspended growth and is in somewhat of a dispersed condition, and then it goes to the clarifier, and we're supposed to produce a clarified effluent. Well, that separation of the treated liquid from the solid then, liquid-solid separation, that's what clarification is all about. That depends then on the nature of the growth that we achieve and the type of flocculation characteristics that are established. So a whole lot of thought is put into flock structure. And you're going to see that when we compare three very good sludges from Trinity River. We've got 10 Mile, we've got Cruise, and we've got D-Cruise, all with slightly different flock structures, all producing very good effluent. They all have good solid separation. Some, we might argue, might be better than others, but that becomes more I'm not sure that there's a lot of value in just besides it's fun to tease each other about who's got the best sludge. I'm not sure that it makes a whole lot of difference between those three plants because they're all producing very compliant effluent with good SVIs. SVI. Anybody define SVI? Sludge volume index. Yeah, it's a numerical score that we put on the sellability so that we can kind of compare one sludge to the next by numerical scoring. And the SVI is just the volume that's occupied by each gram of mixed liquor after 30 minutes of selling. So it's a way of kind of, it's like batting average, something like that. Okay? It's a way of kind of comparing apples to apples. So the bacteria have the responsibility of removing carbon and producing flocks. Nitrifiers are bacteria that are also living right along with those carbon-loving bugs that we call, we use the term here, heterotroph. A heterotroph is a carbon-eating bacterium. A nitrifier is a bacterium that we call an autotroph. It uses an inorganic carbon source. The difference between a heterotroph and an autotroph is one uses organic carbon, the other uses inorganic. But nitrifiers are right there in that same culture. We can hold that, I know I've got heterotrophs in there that ate the BOD. And, oh yeah, there's some nitrifiers in there, yeah. And, oh yeah, there's some phosphorus accumulating organisms. Well, can you really see them? No. But we can see them with tools. And we can see them by inference with results. And by inference, what I mean is we are inferring that they must be there because we see the trail that they lead, the transformation that they achieve, right? So an example would be, you can measure ammonia that comes into the aeration basin, and we can measure the ammonia that goes out of the aeration basin. Ammonia that goes out of the aeration basin is a whole lot less. In fact, it might be completely removed, and something is left in its place. Well, the nitrifiers, let's see now, what was the bug anxious to get or had to get? Had to get energy. It got it by oxidizing ammonia, and what it leaves behind is oxidized forms of nitrogen. So we look for nitrite and nitrate, and lo and behold, by inference, then we know that the nitrifiers are there because the ammonia went away, the nitrate showed up, and that only happens because there are bacteria that do that. Now, Comomox would be one of those particular strains or species of bacteria. Comomox means complete ammonia oxidation. It takes the whole enchilada, of the enchilada being ammonia, and it fully oxidizes it all the way through the two oxidation states from nitrite to nitrate. That's very cool. We got one bug that's a switch hitter. It can do all. Traditionally, nitrification was thought of as being a process that required kind of as Texas two-step, as a tag team match, where you'd have certain strains that could do part of the oxidation and other strains that would do a second part of the oxidation. And that's still true. But we find that there's not, that there are many different strains or species of bacteria that like to get their energy out of that ammonia. And some of them can eat the whole hog, and others have to chop it up into ribs and roasts. Okay. All right. There's also PAOs. A PAO, define that term. A PAO is a phosphorus accumulating organism. Oh, okay. Well, that's another bacterial subcategory here in the whole mix. I can't look at this and see any PAOs, but they are there. See, why would they be there? Well, every bug is there because it's getting what it needs, and that's energy. And the PAO likes to has a particular enzyme set of enzyme pathways that it utilizes to store up food and sequester. We call it sequestering. It sequesters carbon, which is the rate limiting substrate. A substrate is whatever the bacteria acting upon. So carbon ends up being a rate limiting substrate in competition between different species. So basically, hey, whoever gets the food wins. And PAOs, phosphorus accumulating organisms, have figured out a trick to take up and store food. It's like going through the chow line, and they can pack their bag very, very quickly and eat it out on the playground later on. So whoever gets the food wins, and that's what PAOs are good at. You'll hear a lot more about that. So what do the bugs do? They're doing a lot of things. They're removing carbon, they're removing nitrogen, they're removing phosphorus. The protozoa and the metazoa are removing some suspended solids and the dispersed bacteria that fed on the BOD. They're improving the health of the flocks. They're contributing to the clarity of the final effluent. So, a lot of us have spent many years really entertained by and trying to make use of the higher life form picture. And I'm not going to discourage you from continuing to look at your sludge and to celebrate the various big bugs that are there, sometimes literally waving back at us and saying kind of, hey, look at me, look at me. Aren't I big and beautiful? And I'm here to talk about it, kind of thing. I continue to be entertained by it, and I love them, but they are not what's making the whole BNR piece work. They're secondary in importance, but we always like to see them. All right. Well, this is a report that came back. You're not supposed to read all of these names, but this is showing. I couldn't get them all in one graphic. These are the species that were identified, bacterial species that were identified when Mike sent samples out, Mike and Leon sent samples out that came back and said, hey, what's in our sludge? It's like, holy cow. Oh yeah, there's a whole lot there. That's a good thing to have high species diversity, because there is a lot of different substrates that are needing to be degraded that would otherwise contribute to effluent BOD. They might otherwise contribute to effluent toxicity. They might contribute to effluent nitrogen issues. They might contribute to effluent phosphorus issues. Okay. So yeah, thank goodness that it turns out that we have hundreds of species, and that's the normal thing. We've tried to categorize, we put them into buckets. And what we're showing on this graphic is categories that Mike and Leon and Eric developed over the years to kind of take the reports that came back and kind of put these into silos. And so some terminology here that you're going to be hearing about more in the course. AOB refers to ammonia oxidizing bacteria. Okay, there are certain species then that will oxidize ammonia. Oxidation is a chemical transformation of a compound that the bug accomplishes for the purpose of getting some value out of it, and the value typically is that it gets cellular energy. Now, cellular energy is released to the cell by manipulating the cell, manipulate the molecules as it takes them apart. And as molecules are deconstructed by the cell, electrons are moved around. And not get too deep into the chemistry of this, but we'll just say that when we say an oxidation, it's referring to the fact that there's a deconstruction of a molecule, electrons are removed, and they've got to go somewhere. Okay? And so there's electron movement. So the energy is actually electron flow that's actually happening, and it's all very precisely regulated in the cell through multiple steps. And we don't have to get into all of those exactly, but we want to understand a little bit about the principle, because there are things that we measure that determine the health of our biology that is exactly what I'm describing here. And I'll throw out the term ATP. ATP then is a measurement that you will be hearing more about. ATP, check. I think I lost. Check. Is this battery powered? Did I lose a battery?
Yeah, it doesn't have batteries in it.
Check.
I don't remember what goes in the cloud.
Movement of electrons. It's the removal of electrons. Electrons have to go somewhere, and so for every oxidation, there's an offsetting reduction. So there's a balancing of chemical equations here that the cell very nicely manages. So we are counting on growing bugs that can oxidize ammonia. That first step of nitrification, right? If we can find that AOBs are living there. There are bacteria that we call NOBs. NOB, nitrite oxidizing bacteria. Well, the oxidation of ammonia is actually a two-step oxidation. There's enough energy in ammonia that as it's taken apart, it can be taken apart by different enzymes through several different steps. And to get the all of the energy released from that, it has to go through those two oxidation state changes. Okay? So there are species of bacteria that know how to do the second stage of that oxidation. So they work hand in hand. Ammonia oxidizers take it apart the first way, and the nitrite oxidizers take it apart the second way. Right? For many years, then, we tracked AOBs and NOBs because we're trying to get complete nitrification here at the cruise, right? And those of you who've been here for through the years know that when we're doing the first step, AOBs work, we're oxidizing ammonia to nitrite. And if something happens for the second step of NOBs, what is the consequence of that? What do you call it when you get stuck halfway and you've oxidized ammonia to nitrite and it won't oxidize all the way to nitrate? Nitrite lock. If you're taking a certification test, put this in your hip pocket. Remember nitrite lock. Nitrite lock is a half, you're halfway nitrified. Okay, that may not be the way the question shows up. What's the big problem with nitrite lock for us at Cruise? Check. That's it. We're back. What's the big problem with nitrite lock here at Cruise? Thank you, Michael. Chlorine, yeah. Chlorine. How does chlorine work? You put chlorine in water, you dissolve the chlorine in the water, and it forms what ion? It forms hypochlorite, right? Hypochlorite, strong oxidizer, OCl minus. that oxidizing power, that hypochlorite is really looking for something to oxidize. And it finds nitrite and it ties up with it. So the oxidizing power of the hypo goes to nitrite, 5-to-1. For every part of nitrite you got, it's going to take 5 parts of chlorine. Holy cow. If our normal chlorine dosage rate is just a couple of ppm to get proper disinfection, and we've got some nitrite there, it's all gone to the tied up in nitrite rock. And we're piling the chlorine on it, right? So you can see the problem. So the relevance of tracking AOBs and NOBs has been around, one, our interest in getting complete nitrification, and two, managing that doggone disinfection step where there's competition for the nitrite. Right? There's this third category then of buckets that Mike has tracked, in which they identify Anammox and Comomox. Well, these are also organisms that play in the nitrogen cycle and can be of great benefit. And in fact, Comomox has returned millions of dollars to TRA, literally, in savings of aeration energy costs by understanding the biology of Comomox and having the Black & Veatch design team configure the design to optimize the aeration system to create the ecology to grow Comomox. It has completely changed the oxygen strategy and the cost. So this is not just academically, oh, isn't it interesting that these bunch of different names and different functions are there? I mean, it really is. It's just a pure geek. It's like, oh, that's the coolest thing in the world. But if, in the most practical sense, it's making huge impact on the affordability and the completeness of treatment. So, yay for that. PAOs and GAOs. Now these are additional silos that we're actually watching these segments. And remember this sample of mixed liquor that I'm holding up, if you can slice it up, is going to have all of these pieces in here. We're just showing you that what the data analysis has found is actually in there. So PAOs are the phosphorus accumulating organisms. Those are the ones that we're specially coaxing to grow, that will sequester and store phosphorus in excess of what a normal bacterial cell would do. Because phosphorus is a permit issue, right? In the receiving water, in the Trinity River, it's one of the limiting components for water quality parameters. One pound of phosphorus discharge will grow 117 pounds of algae. The conversion of phosphorus to algae is remarkable. So it doesn't take much to trigger the eutrophic. So certification test, eutrophication, if you see that term, that's the nutrient enrichment of a receiving water by nutrient addition. That's kind of a loose definition of it. But if you hear eutrophication, they're talking about, hey, we're growing algae because of nutrient enrichment. That's what we mean by that. So phosphorus accumulating organisms are something then that we really are putting a lot of our thinking around and our operational practices to exploit. And the reconfiguration of the crews with the addition of the anaerobic selector at the front end was exactly for that reason. It created then the ecology necessary to select for organisms that can take up and store phosphorus. And we'll get into how that happens, but the fact is we're targeting the adaptation of the microbiology to grow a strain that was always there in very small numbers, but now we want to increase its percentage of. Okay, so these organisms are, we say, ubiquitous in nature. Ubiquitous means they're everywhere, but what we're doing is we're selecting for and improving or enhancing the numbers of them. so that they actually can move the needle and make a difference. GAO is a glycogen accumulating organism. Well, who cares about GAOs? Well, the only reason we give them so much attention is because they like to eat the same things that PAOs do. They're looking for basically the same lunch. But the glycogen accumulator doesn't store phosphorus like the phosphorus accumulator does. So it's like they suck up the carbon, but they don't give you the phosphorus uptake in return for that. Well, dang, that robs then the PAOs of their full function. And so we're just trying to understand how to control then the operational pressures to be more favorable in the competition between PAOs and GAOs. Okay? And we're measuring those both. OHOs. This is why the Campbell's alphabet soup metaphor is in my mind. It's like it's all these letters, it's like decode this thing. OHO just means other heterotrophic organisms. Well, that's the lion's share of all the bacteria that we haven't put into these previous categories. It's probably by weight, about 85 or 90% of all of what's in there are other heterotrophic organisms. So it's the several hundred other species that are the other heterotrophs. And then because they've been relevant at TRA, we paid attention to quantifying the amount of zooglia. Zooglia is a flock-forming bacterium. It's found in almost every activated sludge. Zooglia remigera has been shown and been reported in the literature for decades and decades and decades. So it's nothing new there. The relevance of zooglia is that organism, all the bacteria, I'll digress for a second. All of the bacteria that are flock formers actually are flock formers because they excrete an exocellular, exo outside cell, They excrete an exocellular polymeric substance. We call it EPS, or we can call it slime. You can call it bug snot. You can call it bug blubber. You can call it anything you want. But you get the idea that it's the sticky, gooey stuff that makes activated sludge slimy and stick to the surfaces and allows attachment. Okay, so bacteria produce slime. Zooglia happens to produce quite a bit of it, thank you very much. And so when that fraction of the microbial community is blooming and we're getting lots of zooglia growth, we're getting lots of that slimy type of growth with it. And when we get lots of that slimy type growth, it does impact the settleability of the flocks in the secondary clarifier. It can also affect the dewatering properties of it. Okay? So we say, well, so we want to make bacteria that don't make too much slime. Yeah, that's true. Turns out that the slimes that are made are not all the same composition. In other words, different species of bacteria make slimes that are of actual different chemical composition. The slime, the EPS that's formed is actually contains protein molecules, it contains carbohydrate molecules, and it contains lipids or fats, right? So there's proteins, sugars, and fats in different molecular arrangements that make up the biological slime capsule for each of the different species. So it really becomes a little bit of a can of worms in understanding the problems with zooglia and its slime. But the fact is, zooglia makes a particular type of slime that makes it very low density and tends to create then what looks kind of like a straggler flock in the secondary clarifiers. And it doesn't provoke horrible effluent TSS, but Mike is the kind of guy. Well, Mike has a calibrated eyeball. Most people who've been around Mike know this about him. If you've ever walked across out to the secondary clarifier with Mike, Mike will look at the effluent and secondary clarifier and look at the mixed liquor, and with his calibrated eyeball, he will tell you what the TSS concentration is. And it's as good as any lab analyst I've ever seen running the lab test. So Mike will, takes issue when he's got a couple of ppm of TSS going over the secondaries. And we've looked at this microscopically, and we know that it's not all of the zooglia, but a good portion, of what's actually segregating there is that carryover. So for good reasons, we do try to pay attention to that. And we'll be saying some more things about this, and Leon and Eric, certainly in their part of the course, will be talking about the events that trigger then the propagation of higher than normal zooglia. And it does have to do with the volatile fatty acid variability of the final effluent and what might or might not actually be removed in the selector. And I know I'm giving kind of a complex lead-in to what my colleagues will be talking about. But more to come on this. But zooglia is something that we have tracked. Of course, filaments refer then to the type of bacteria that don't grow as flock formers. They like to grow end to end as long strands. They're always associated with flocks because they grow within the flocks, and they're always part and parcel with flocks. But for those on the internet, you won't see the model I'm holding up here, but for years I've carried around sponges with little bamboo sticks in them to illustrate flocks and filaments, right? And what we're trying to illustrate here is the fact that filaments can become a problem when they interfere with the close approach and compaction of adjacent flocks. So filaments are something to be mindful of. By and large, they're positive. They're typically more positive than negative. They're positive because they provide some structural integrity to flocks and make flocks withstand the shear forces of pumping and aeration. So that's a positive. Where they're negative is when they're growing in great abundance and there's such high volume to the number of filaments or filament abundance that the flocks in the secondary clarifier can't tighten up because they're physically held apart from each other, right? So we do keep track of filaments. There are several filaments that are also have been a little bit of our bane because they cause foaming. The greasy chocolate mousse looking character to activated sludge foam is sometimes related to the growth of a couple of different filaments. Nocardia, which is in the Actinomycetales family, is, or we'll call them Nocardia-like filaments. We've had off and on, and it's very hard to find an activated sludge plant that hasn't had some Nocardia from time to time. I didn't see any real problems in the 3 samples that I looked at in preparation for this course. 10 Mile had a little bit. I took some micrographs of it. I did not put it in the report because it wasn't really anything other than just a typical example of a small amount of Nocardia. Just was there. BNR plants are plagued from time to time with the growth of Microthrix parvicella, which is another species of filament. It grows really more like coils of rope. And I'll say more about that as we get down the road. So we do pay attention to filament abundance. One of the things that has really been remarkable as plants have shifted from conventional activated sludge to BNR, because BNR incorporates then pressure points where we're actually selecting for competing species. It's largely deselected the growth of filament. So many filamentous problems have been mitigated by BNR designs. Not all of them, but certainly the SVI now, the sludge volume index numbers that we get on BNR plants are vastly better meaning there are lower SPIs, the sludge settles and compacts well. Vastly better than conventional designs as a large body of data would show. And then the foam-causing bacteria, this is referring to the Nocardia type foams. So when you've sent samples out, you've come back and you get categorization that goes that way. All right. This is some TRA data then that shows the categories I just listed along the bottom of Animox, AOBs, NOBs, filaments, foam, GEOs, PEOs, and zooglia. And the red bars indicate the counts that were made when this plant was changed to a BNR configuration by the addition of the selector at the head end. The blue bars show the counts of those, the relative counts, when it was a straight nitrifying activated sludge system, which was kind of a plug flow type of reactor operating with an SRT and DO control to achieve nitrification, but without the anaerobic selector going for phosphorus removal. And really what was being targeted there was to get better P removal. And you can see it on the data where the PAO column showed the higher counts. What also occurred was you had some mitigation of the zooglia as a result of that. Now the reason for that, at least my opinion on that, I'm not sure, I really haven't discussed this with my colleagues, or maybe I did, but I forgot, and I forget a lot of stuff. But out of the gate, I would just say that we know zooglia likes readily degradable carbon. It likes the soluble, readily degradable COD. And so if there's less of that available, we ought to grow less zooglia. Simple as that. Readily degradable COD, another term we might use for that, and you will hear that, is VFAs or VOAs. VFA is volatile fatty acid, right? VOA, volatile organic acid. We're talking about the low molecular weight organic acids, acetic acid being the principal example of that, right? So if we're selecting for PAOs, what we know about those is they just suck up VFAs. They take that readily degradable COD, and that's what they sequester as a carbon source. So if the PAOs are taking it up, it must therefore not be bioavailable to something else, and the something else was the zooglia. So the zooglia went down because the PAOs went up. So you're kind of inferring a shift then in the substrate. What we're shooting for is we want more of the guys that hold on to the phosphorus, and they got that. All right. So the bacteria, the bacteria are the primary biodegraders. They're also transforming nitrogen and phosphorus. They're single-celled and they reproduce very fast. They can reproduce fast because they just do it by themselves. There's no dating app. There's no courtship. There's no Tinder or whatever however it's done these days. I don't know. But in any event, binary fission is the means of reproduction. So a bacterium, if it has all that it needs, in just a little bit of time, it's going to make another one. So it's going to duplicate its chromosomes, split up its important cellular parts, and away you go. So 1 becomes 2, 2 becomes 4, 4 becomes 8, and you can, and this is what we would call logarithmic growth, and you can go from 1 cell to 1 million in a very short period of time. So when we're seeing populations rise and fall, it's very simple reproduction. And so the ability of that microbial culture to respond fairly quickly and build numbers up or have them diminish goes to the fact that it's a pretty efficient type of reproduction. Right? The bacteria are producing their energy in the form of ATP. ATP is a universal biochemical, adenosine triphosphate. It's a molecule that is common across every living organism that ever existed. And it's the same molecule. You and I, every cell that we have that's firing is doing so because it's firing, it's getting its energy from ATP. And that's the same mechanism that the bacteria are getting their energy, is they're generating ATP. So the ATP is being made, it's being used, it's being made and used in a very rapid cycle. So in my 74-year-old carcass, let's say I weigh 200 pounds. I'm working on that. It's not quite that much anymore, but the math makes the math easy. I weigh 200 pounds. I got 200 pounds of cell mass. I've got somewhere in the neighborhood of 10 trillion cells making it that cell mass. In my carcass, I've got a half a pound of ATP on board. And in a 24-hour day, it turns over a number of times. It turns over about 400, the average human being, at least as often as 400 times a day. That pool of ATP, that half a pound of ATP in those cells is turning over 400 times. Get out your calculators and calculate what's 400 times 0.5. 200. My point is, I'm making my body weight in ATP a day. And my body weight's not changing. The point is that that molecule is active and a live mass is live because it is continuing to have electrons flow that crank out and generate the ATP. And that ATP is what allows a neuron to function. It allows a cardiac muscle to twitch. It allows every cellular function that requires energy. That's what makes it happen. Okay? So we understand the universality of ATP, and then we use ATP measurements then in characterizing your slides. So you're going to see as we go along, we do ATP measurements from time to time. We look at the amount of oxygen that's being taken up by your sludge and the amount of ATP that's being produced. And from that, we can determine a little bit about, is the condition of the biology good? Okay. So ATP, cool thing to know about bacteria. All right, a little bit more about the bacteria. Terms, catabolic, anabolic, and metabolic. That's referring to really kind of the metabolic scheme of things. Catabolic is when we're breaking things down. Anabolic is when we're building things up. Well, a cell has to do both, right? We talk about our metabolism, but it's really, metabolism is the sum of what we're breaking down and what we're building up, right? If we're building bacterial cells, then let's remember that they have a chemical composition, right? There's carbon, oxygen, hydrogen, nitrogen, phosphorus in all the bacterial cells. And so when we're looking at biological nutrient transformations, part of that is just the fact that you're growing something that has a place to put all of those atoms. Catabolism releases energy, and it does so by oxidation reactions, which is a loss of electrons. And for every oxidation, there's an offsetting reduction. So basically, and I've said this earlier, so I'm not going to belabor the point, electrons are moving along. And for every oxidation, there's an offsetting reduction. So you and I, of course, human beings, we have an energy need that is being met by the blood supply that is flowing around and delivering energy to all of our cells. And we have a simple sugar that flows around through our bloodstream. What's the sugar called that's in our blood supply? Glucose. And some of us are paying more attention to glucose than others. I want everybody to pay attention to glucose, or to at least understand it, right? Glucose is kind of our universal energy molecule. And so we're delivering that energy to our cells. And what is it that we take in? We're breathing in what? Oxygen, and we give off carbon dioxide. Thank you. That is cellular respiration. This little equation under C6H12O6, that's glucose. That's what's in our bloodstream. Oxygen is what we take in through our lungs. Carbon dioxide and water is what we're exhaling. Well, we didn't do this thing just to see if we could do it. We did it because we needed the energy that comes from it. We needed the ATP from it, right? So what we're learning about the bugs has a very direct applicability to what it's useful to know about ourselves and how our own physiology works. ATP then, just quick review, is a triphosphated. There are 3 phosphates stuck on that molecule. We don't have to get very far into the chemistry. Just say that terminal, the third phosphate on the end is the one that comes off and releases energy when that bond is broken. And when it drops down from ATP, it goes to ADP. It's diphosphated. And that ADP cycles back up to ATP. And so there's a continual cycling in the cell between those two. Net production of energy from that cycling, covered that. One of the things that I have found useful to know then, as I've studied ATP and done a lot of these measurements, is that it is used in the cell for different purposes. The first thing that the energy goes to in the cell is for maintenance. This is just to maintain the mass that's there. Okay. The second purpose that the bug would use ATP for then is to make more of itself, make babies. Okay. We won't get cell growth unless there's enough energy to allow it. First, you got to stay alive, then you get to move on and make more cells. And then if there's still enough energy available, it goes into things that are not absolutely essential to cell survival, which is the production of the energy that goes into the production of extracellular polymers. Okay. So the bacteria maintain themselves, they reproduce, and they make slime that allows them to stick one to the next. All 3 should go on all the time, every day. No separation between duties. Okay. Normal activated sludge is always going to do all 3. They eat their food, and they make slime, and they flocculate, and treatment is done. If something interferes with metabolism, and this is where our industrial pre-treat ordinances are trying to protect us from problems that come down the lines. It's where chemical interferences and disruptors occur that cause what we call uncoupling, where the normal electron flow that makes the ATP happen, something short circuits and those electrons can't get all the way to the end and make enough ATP. So in other words, it's running ATP short. Okay? And that actually happens. It happens actually fairly frequently, but it doesn't persist, so you never see it. It's just like, gee, the sludge kind of looks sick today. I wonder what happened. You never know. Tell us sometimes we do, right? But one thing to look for then is if I have some persistent impairment of energy flow in the cell, I start to see less polymers produced. So the sludge starts to deflocculate and get turbid because it's not making the normal glue. Make sense? What we also see is the mixed liquor doesn't increase in concentration like it normally does. I'm not growing as much sludge. You may be removing BOD, but it's not growing sludge, it's not flocculating well. If we're not growing sludge, it's also not removing the nutrients that it would have removed that grew that sludge. So there's a ripple effect of running low on energy. A very well-known uncoupler that does exactly this is a compound called dinitrophenol. Dinitrophenol was discovered to do this back around World War I era. It was discovered by folks that were on the East Coast. There were workers working in a factory that was making bombs for the war effort, TNT. And one of the precursors for TNT was dinitrophenol. Workers that worked in this factory were going to the doctor complaining of weight loss, excessive sweating, general malaise, or just feeling down, low energy. And the doctors said, kind of shortened the story up a little bit, but it's like, so what's this yellow powder on your clothes and on your hands? Oh, well, we work down at the TNT plant, you know? And Doc says, so let's wash your clothes, wash your hands, wear PPE, don't breathe this stuff, keep it off of you, don't expose yourself to that. And they got better. And then somebody had the bright idea that, hey, maybe we could use that stuff for a different purpose. Because obviously it was causing some sort of metabolic slowdown in energy. You know, people were running a fever, losing weight. Maybe we could make that into a drug that causes weight loss. And they did. And you could buy over the counter dinitrophenol in drugstores. And it was sold hundreds of thousands of doses of this for a number of years. It was a weight loss drug. But it does uncouple electron flow in the liver and in other cells, and you don't quite get as much ATP, so you don't have as much energy, you lose weight. Yeah, you run a little bit of a fever from time to time, but you lose weight, and there were not other apparent persistent effects until there was. And people took more than they should, and they died because there was so much energy being shed because it couldn't make ATP. It's shed as excess heat that it cooked the brain. Temperature went up to 106 in people, and that's fatal. Holy cow, this weight loss drug will kill you. Yeah, it will actually. And the first drug that was banned when the FDA finally had regulatory authority was that drug. Came off the market. So this uncoupling piece, I don't know if that story is interesting or whatever, but the fact that it's been well known in human physiology, it is universal across all biological systems. We see it a lot in wastewater. We suspect a lot of it in wastewater. We see it when we know what to look for. Mike has experienced this here. Certainly he has a lot of experience with it. My first experience with it was 20 some years ago in a plant that was had AFFF coming in. AFFF is a firefighting foam, anionic firefighting foam, causes uncoupling. There are a number of compounds that will cause that type of thing. So I won't say more about it other than we're getting kind of into the depths of a little bit of metabolism and biochemistry to try to give you some foundation to understand when we're talking about bugs are transforming things through normal pathways, there are interrupters that go along there. And understanding how ATP plays a role in that, I think is part of the story that we have learned here in Texas that we're trying to share with others. You've been sitting for a bit over an hour. I'm going to give you a 10-minute break here, then we'll come back.